All right, so chapter 21 is all about carboxylic acids and carboxylic acid derivatives. It actually includes things like esters, amides, nitriles, anhydrides, a lot of different functional groups. The main unifying theme for this chapter is they all have the same oxidation state. That's why you lump them into one massive chapter. So we're going to start off first by doing nomenclature with carboxylic acids, because it is a little bit different. And we'll do a really simple one at first, and then we'll go into the special cases. So just like with all organic naming, you want to identify the longest continuous carbon chain that contains your functional group. And you want to have your functional group at the lowest position. So you can tell the backbone for this carboxylic acid is a hexane derivative. So when you go to name this, you're still going to have hexane as your prefix to indicate all 6 of those carbons. And then for your suffix, you're going to change this to an oic acid. So that's really the base naming for most carboxylic acid derivatives with a few exceptions. And so we'll go into some of those exceptions that are more common. So we'll do other IUPAC accepted names. All right, the first one is the simplest carboxylic acid, and it's kind of half aldehyde, half carboxylic acid. This is called formic acid. And what's that? Oh, IUPAC, there we go. And formic acid, if you look at the functional groups, the carboxylic acid takes higher priority than the aldehyde. That's why the suffix ends with an ic acid. If you've ever smushed ants and then smelled your fingers, it has that really pungent smell. That's actually formic acid. It's a defense mechanism that some insects use to scare off predators.
Is that also, because that also smell like penny, right?
I don't think they normally use it in penning. It's like a very pungent acidic smell. So if you ever want to go outside and smush ants, I guess you can smell your fingers afterwards and get a rough idea. All right, the next one is pretty similar, but with a methyl group. If you went around and called this ethanoic acid, people would look at you funny because nobody calls it that. People call this acetic acid. And acetic acid also goes by another name. Does anybody know what it goes by in the kitchen? Vinegar, right? So it's used in cooking all the time. Then there's some longer chain ones. Again, this one, if you called it propanoic acid, most people would kind of look at you funny. Most people call this propianoic acid because it flows better. I don't know why. I didn't make these rules. So not propanoic acid, propianoic acid is what most people call that. The next one. Yeah, maybe. They're like, at this point, I'm not going to change it because I'll look stupid, so it's propianoic acid from now on. All right, next one. Most people don't call it butanoic acid. They call it butyric acid. Has anybody seen the show Whale Wars on Animal Planet?
Yeah.
It was popular for a while, but there's a group of people that go around and harass these Japanese whaling ships. They claim they're hunting whales for research, but it's a lot messier than that. But anyways, one way they try to get them to stop whaling is by hucking bottles of butyric acid at the vessel. The reason they do it is this stuff stinks to high heaven. That, and if they manage to land it in whale meat, they can't sell the whale meat as food because nobody wants to eat this stuff. It's disgusting smelling. Yeah, you can clear out a room by opening a bottle of this. All right, there's a few other ones. This one you already know. What's this called? Benzoic acid. And then the last one that's presented in our textbook is a cyclohexane derivative. And this is just called cyclohexane carboxylic acid. Whoop. It's like they just gave up trying to name it. Yeah, exactly. All right, so those are the common acids that don't follow the traditional IUPAC naming system. In addition, we also have diacids, so where you have two carboxylic acid functional groups, and those are more common in biology. So I did want to present those for those of you going on to biochemistry. And the first one is the simplest diacid, where you have two carboxylic acids. And this is called oxalic acid. Next one is with one extra carbon in between. This is called malonic acid. Whoop. Next one, you add one more carbon. This is succinic acid. Next one is with one more carbon. This is glutaric acid. And we've got another one with 6, and then we'll stop after one more after this. So 1, 2, 3, 4, 5, 6. Does anybody remember the name of this one? Way back to second term, our first lab, we ring open cyclohexene and made what? Adipic acid. And then we've got one more. Got 2, 4, 6, 7 carbons. This is camelic acid. Whoops. These obviously don't follow the IUPAC naming system, but I've got a really good mnemonic that'll help you remember these. And this is what I used in undergrad. Oh my, such good apple pie. So oxalic, malonic, succinic, glutaric, adipic, and camelic. So if you ever forget these, you can just write them out in order and try to remember the name using this. A lot of these are common in biochemistry as a part of various biochemical cycles, so it is important to know these, especially for biochemistry classes. Does that make sense? It's a useful mnemonic, honestly. I still use this because sometimes I forget. I'm like, what's the one with the G? Oh yeah, it's that many carbons. So it's a good trick. All right, carboxylic acids are pretty unique. We're not going to go super far into them. There's two main things to remember about carboxylic acids. The first is their relative pKa. So if you remember, the pKa of water is about what? It's about 15, give or take. So pKa of water is about 15, and pKa of a carboxylic acid, on the other hand, is about 0 to 5. The question is, why is there such a big range, 5 orders of magnitude? So one carboxylic acid could be 10,000 plus times more acidic than another one. What could change the acidity of a carboxylic acid? Resonance? Yeah, so maybe this R group, if it's an aromatic ring, that could definitely change it. What else?
Polarity.
So there's the same polarity for all carboxylic acids, but there's another term that's used when you've got electronegative atoms multiple bonds away. What do you call that? Induction, or the inductive effect. So you can have a huge range of pKa values if, let's say, there's a trifluoromethyl group versus a regular methyl group. All right, the other interesting thing with these is they're really, really, really good at hydrogen bonding, which some of you have seen in your IRs for this synthesis lab. A lot of people were worried they didn't make their product because the OH region was so broad. And the reason for this is you actually get a dimerization effect where you can have a hydrogen bond to a second carboxylic acid on both the top and the bottom. That leads to a huge broadening, both in IR and NMR. So typically with IRs, a pure carboxylic acid samples, the OH frequency doesn't absorb very much and it's very broad. Same thing with NMR, the OH peak oftentimes is so broad you actually can't even see it because those protons will exchange out. So it is a unique property for carboxylic acids, and it makes those OHs very different than normal alcohols. Make sense? Okay, so now we've got to review preparation of carboxylic acids, and a lot of this will be reviewed from second term. So let's do a little bit of review, and I want you to help me remember the reagents. So let's say I've got a primary alcohol and I want to make a carboxylic acid. What reagent should I use to form a carboxylic acid from a primary alcohol? What's that? Chromic acid, absolutely. So if we do that, that's commonly done with sodium dichromate and sulfuric acid and water. So that's one way to do that. That was section 10.9 in your textbook if you're a little rusty on it. All right. We also saw during second term a way to turn benzylic carbons, those are those carbons right there, into something like benzoic acid. What reagents can we use for that? You can use chromic acid. It's not that common though. What's the other one that can be used? Yeah, KMNO4. I like how you mumbled that so you wouldn't be called out if you were wrong. Most people don't use chromic acid because chromium waste is really hazardous and very expensive to dispose of, where potassium permanganate, it's not perfect, but it gets the job done and it's not going to give you cancer. You also need sodium hydroxide, water, and you'd normally heat this to reflux for a while. And then at the end, you have to reprotonate your carboxylic acid, so you treat this with strong acid. This was section 18.6 in the second edition textbook. All right, again, going back to second term, we saw we can make carboxylic acids from alkenes. Specifically, you can make 2 carboxylic acids. So if those R groups are different, you can make 2 different ones. If they're the same, you're going to get 2 identical ones. What reagent do we need? Ozonolysis, so ozone and water. And unlike with alkenes, you can actually do this in one step. You don't have to have DMS or zinc or any of that stuff. This was section 10.9. You can also do this with nitriles. And you can change a nitrile into a carboxylic acid. And in fact, this is your pod. So it's good practice. A lot of the proton transfers are very, very similar to last chapter. So what do you think you probably want to do? You probably want to protonate one of those double bonds, and then your goal is to kick off nitrogen as a leaving group, so you're going to kick off ammonia in this reaction. So acid and heat can be used to convert nitriles to carboxylic acids. And then we also covered a new one this chapter. This doesn't have to just be a benzoic acid. It'll work with any aldehyde. And we can change this to a carboxylic acid easily. Whoops. And this was one of your exam problems. What reagent do we need to accomplish that transformation? Yep, RCO3H, our peroxy acid. So this was the Baeyer-Villiger oxidation. This was in chapter 20. That was the last chapter that we just covered. Make sense? Yeah.
So is it all right? I think that basically if we let's say if we're not being specific by just saying R.
Yeah, you can say R. The reality is there's a huge variety of peroxy acids you can use. So peroxyacetic acid is one of the most common ones because it's cheap. It has a high atom economy, and the byproduct's acetic acid, which is really easy to wash away. So that's one of the more common ones. All right, there's a new method I wanted to show you that's really useful. And it's actually one you probably know how to do already in terms of its mechanism. And that's using a Grignard reagent. So if you look at this transformation, we're starting out with the Grignard reagent, and we're making it into a carboxylic acid. If you look at what we're adding in, we're adding a carbon and 2 oxygens. So all you really need to do is huck in some dry ice, CO2. And then when the reaction's all done, to ensure that it's protonated, treat it with strong acid. So it's a really simple transformation that can be done with dry ice in a lab with the Grignard reagent. So let's try to rationalize the mechanism for this.
You want to say CO2 is solid, but it can be a gas too, right?
Yeah, most people, though, will imply that it's a solid just because it's easy to get. You could theoretically do this with the gas. It's just way more work and effort than it's worthwhile. You can buy CO2 for like $1 a pound at Fred Meyer, so there's no purpose of getting a big CO2 cylinder. All right, so mechanism. We've got CO2 here. If you remember, you can show this as a strongly polarized bond, or you can show it as ionic. I'm fine with that either way. And this carbon almost behaves like a negative charge. It'll attack the central carbon and carbon dioxide, kick up electrons to the oxygen. Makes sense. You end up forming a carboxylate salt. Which is why in your second step, you need to treat this with a strong acid to ensure that your carboxylate salt is getting protonated and you end up with your neutral carboxylic acid. So it's a pretty useful technique, especially if you want to convert an alkyl halide into a carboxylic acid, is you first would say, all right, I've got my alkyl halide right here. I can change this into a Grignard reagent by adding in magnesium and ultimately convert an alkyl halide into a carboxylic acid. So it's a very useful tool in synthesis planning. Does that make sense? All right. Now we've got to look at reactions of carboxylic acids we just did preparation of. And again, most of this is going to be review. But I think it's good review, especially for the ACS. Let's say I have a carboxylic acid and I want to go to a primary alcohol. What reagent do we need? So PCC is an oxidant, other direction.
Yeah,
LAH, exactly. Sodium borohydride doesn't have enough oomph to accomplish this, so you have to use a stronger reducing agent. So lithium aluminum hydride. That's step one. This is a really, really strong base, so you can't run this in an alcohol solvent, which means in step two, you actually have to add in a proton donor. Something like weak acid or water is typically shown. When we covered this, we didn't actually do the full mechanism. So what I wanted to do is briefly take a look at this mechanism. I don't know why you didn't present it in the alcohol chapter, but just chose to put it off till this chapter. And the first step in this reaction is the reaction with lithium aluminum hydride. And like I just said, lithium aluminum hydride is a really, really good base. So what do you think is going to happen first? Yeah, it's going to act as a base. deprotonate your carboxylic acid. And then you've got this aluminum complex floating around. And this is where weird stuff happens, right? So the first step is that aluminum is sp2 hybridized, right? It means it has an empty p orbital. It wants electron density from one of those oxygens. So in this case, the oxygen can attack into that empty p orbital. And then when that happens, the hydride will actually get shifted over immediately to that central carbon. So it looks way different than the one with aldehydes and ketones. Oops. So now you've got the aluminum covalently bonded to the top one. Whoops, I forgot an arrow kicking up electron density. There we go. We added in a hydride to that central carbon, and we still have this oxygen with a negative charge hanging out here. During this step, this actually acts as a good leaving group, this entire functionality. So you can clamp down and kick this off. And you actually go through an aldehyde intermediate when this happens. The tricky thing, though, is when we look at our starting material here versus the aldehyde, which one's more reactive towards reduction? The aldehyde, definitely. So you can't stop here. Even if you form a little bit of it, it's immediately going to be reacted with any excess lithium aluminum hydride. So uncontrollably in the next step, you'll continue reacting this, where another equivalent of lithium aluminum hydride will attack in. It's for this reason that most of the time you see this reaction, it's done with excess. And then last but not least, we react this with a strong acid, or even just water in some situations, to give you your primary alcohol. Does that make sense? Part of the reason that sodium borohydride isn't used here is you do need that aluminum to act as a strong Lewis acid. So that step in the top right-hand corner, you want electron density to be dumped in. The sodium borohydride doesn't have enough Lewis acidity to accomplish that step. All right, there's actually another reaction that is pretty common that does the same thing. We'll look at the alternate reduction. And this is one where we're not going to show you the full mechanism, but it's very powerful. You can use BH3-THF. And you can get this to reduce all the way to a primary alcohol. The nice thing with this one is it only works with carboxylic acid. It doesn't work with aldehydes, ketones, esters, or anything like that. So I'll show you an example of this in action.
You still use peroxide?
No, it's actually just one step. Yeah, so no peroxide in this one. Good question. So if you run this reaction with BH3 PHF complex. This whole side right here is going to be unreactive. So you can leave the ketone as is and only reduce the carboxylic acid side. If you think about trying to accomplish this using the chemistry that we learned previously, there'd be no way of doing it. So this is a pretty clever workaround for that problem before.
What about esters?
It won't react with esters. It only does this with carboxylic acids. Good question. All right, the other reaction that we did learn previously with carboxylic acids was using them as nucleophiles. And this actually goes all the way back to first term. But we know how to convert a carboxylic acid all the way to an ester. So carboxylic acids, when they're protonated, are really crummy nucleophiles. So the first thing we've got to do is get rid of that proton. So most of the time you'll see something like sodium hydroxide used because it's a cheap base. Once you have the carboxylate salt, now all of a sudden you've got a negative charge on that oxygen. It's a pretty good nucleophile. This can attack that carbon and kick off your leaving group. The key with this is this has to be a very good electrophile. So what do I mean by saying a good electrophile? What would make it good? There's a bunch of different things we can look at. First thing is leaving group. Has to have a good leaving group, right? That's one half of the electrophile story. The other half is sterics. If this is sterically bulky at all, this reaction will not work. So typically you want this to be a primary or methyl with a good leaving group. This is more finicky than most SN2 reactions, and that is because this isn't a very good nucleophile, right? It's resonance stabilized, which means your electrophile needs to be that much less stable or more reactive. So that goes back to first term chemistry. Make sense? Okay. Now what we've got to do is start talking about all the derivatives and offshoots of carboxylic acids, and I don't think we're going to get very far today. But let's at least get a good list going. And like I said, he organizes this chapter based on oxidation state. So as a bit of review, let's try to determine the oxidation of the central carbon. And assume the R is another carbon. So carbon normally has an oxidation state of 4. How many electrons does it have when we follow the rules we learned? So remember, if you've got an electronegative atom like oxygen, it's going to hog all of the bonding electrons. So really, this one has an oxidation state of +3. It'll share the electrons in that bond because it's a tie between two carbons. So it's a high oxidation state, and really, when it comes down to it, as long as you have an electron withdrawing group coming off this position, this also has a +3 oxidation state, right? So he lumps all of these together because they have relatively similar reactivity due to the similar oxidation state. So let's take a look at similar examples. And so we need to find some common electron withdrawing groups that can be in that position. and I'll try to order these very specifically. The first one is with halogens, and typically the only halogens you'll see are chlorine and bromine. You don't see fluorine and you don't see iodine really at all. However, I think one of our pods later, I might throw in an iodine at you and see if you can figure it out. Does anybody remember the name of this generic functional group? So let's say it's a chlorine. It's referred to as an acid halide. So if it's a chlorine, it'd be called acid chloride. If it's a bromide, it'd be acid bromide. Okay, so that's one of the most common ones that you'll see. Next one's also a throwback to first term. We haven't really seen this functional group since fall. What's this functional group called? Starts with an A. Anhydride. So that's pretty common. Both of these have this electron withdrawing group coming off that same position, right? So the central carbon has an oxidation state of +3. Next, we've got esters. Same thing, electron withdrawing group there. After that, we've got a slightly less electron withdrawing group, the nitrogen derivative. This could be any amide. And then last but not least is the oddball that doesn't really fit the other trend, but these are called nitriles. And they have that nitrogen doing the electron pulling. The nice thing with this is the trend is easily explainable. As you go up this list, they are more reactive. Does anybody know why? Resonance? That's actually part of the story with anhydrides. Think about it this way. The parts I circled in green, you can almost treat as leaving groups, right? What makes a good leaving group? It's stable when it pops off, right? So a halogen, when it pops off, is very stable, right? We know that sodium chloride, the chloride is stable. It should be in ocean water, hopefully. Anhydrides, if you pop those off, you have a carboxylate salt. The negative charge is on an oxygen. That's good. And it's resonance stabilized, even better. Next one is esters. You don't have that resonance stabilization, not as good. Amides, even worse. Nitrogen doesn't like a negative charge. And then even worse after that is nitriles. So the general trend, it follows the same trend as with leaving groups. So I'll just say same trend for leaving groups here to remind you. All right, we've got about 10 more minutes. So we'll do a little bit of nomenclature and no more reactions. So we'll start with acid halides first. And the general trend is that you have a YL bromide or chloride suffix. So I'll show you a few examples. We'll compare the parent carboxylic acid with the acid halide. So the one on the left has 6 carbons. We previously said that you always start with the prefix, which in this case is going to be hexane. And then we have the oic acid suffix for carboxylic acids. For the next one, what we do is we still have hexane, and then we go oil chloride. So you do have to change the suffix to that YL. Let's try another one. Yeah, carboxylic acids take precedence over aldehydes and ketones. Yeah. Yep. All right, what's this acid called? Acetic acid. In this case, what you would do is you would chop off the ick and the acid, and then we could turn this into something like an acid halide with the chlorine coming off of it. And this would be acetyl chloride. So again, we're swapping it off with the YL and then the chloride. Does that make sense?
It's a Cl replaced with bromine. It'll be acetyl bromide.
Acetyl bromide. Yeah, so it has the IDE suffix. All right, does that make sense? We're not going to get into all the wacky order of priorities. It's just important to remember that these have the highest priority out of all the other functional groups we've looked at so far. So as far as we're concerned, try to stick with these parent names. And hydrides are pretty straightforward. And hydrides are the next most reactive. These are the easiest to remember because you just change the suffix to an anhydride. So I'll show you a few examples of these. So like I said, this is acetic acid. So what we're going to do is we're going to swap off the acid for an anhydride. Typically, when you see anhydrides, they're going to be symmetric for the most part. So this is just called acetic anhydride. Easy enough. It is trickier though if you have non-symmetric ones, so I'll show you the simple trick for determining how to do that. These aren't as common, they're logistically harder to make. But essentially you can do this by kind of imagining what two pieces it takes to make them. So if we mush these two pieces together, we'll get an anhydride with an oxygen in between both of them. And if we look at the starting material on the left, that's benzoic acid. This one's acetic acid, which means the final name is going to be acetic, benzoic, anhydride, because it's a mishmash of those two acids that are used to make them. Does that make sense? Yep. Yeah, exactly. So in this case, we put acetic first because it has the A, and the A would come before the B. Does that make sense? All right, I think we might stop there today, and then tomorrow when we come back, we'll finish up with naming esters, amides, and nitriles.